Alright guys, welcome to Graphing Radical Functions. First things first, this is probably the best handwriting I've had all year. I'm pretty sure it is. So we're going to talk about graphing radical functions. We've done all this simplification, solving radicals, and it's really the same for each family of functions in Algebra 2. You get you started with quadratics, you learn how to factor them, you learn how to solve them, you learn how to simplify them by multiplying and performing operations on them, then you learn how to graph them. And now we're in radicals. We've done the same exact thing. We've learned how to simplify, multiply, divide, add, subtract these radicals, simplify them using rules. And now we're actually going to graph them and see what they actually look like. So the essential understanding here today is that you've got to know that the square root function is the inverse of a quadratic function that has a restricted domain. So that's really important. Okay, and these next two bullets will kind of address this. So the square root is the inverse of a quadratic function, bottom line, but it has a restricted domain. And when I talk about a restricted domain, the inverse, the square root function, is a restricted domain. The idea here is that f of x equals x squared. This is just the parent function. This fails the horizontal line test, meaning if you draw a horizontal line that was vertical, horizontal line through your parabola, it hits it in two spots. So what that tells us is that it fails the horizontal line test, meaning this is not one-to-one, so that means the inverse is not a function. Okay? So you got to think about that. Although f of x equals x squared, because it's a function because it passes the vertical line test. This same function fails the horizontal line test. And when you fail the horizontal line test, your inverse is not a function. So by restricting the domain of your function, the quadratic, we can show that the inverse is a function. Okay, and I'll show you what that looks like in the second slide here. So here's four graphs. And this is the standard f of x equals x squared function, the parabola from -2 to 2 there. That's all I drew. There's our parabola. Now, this is what the inverse would look like. So f of x equals plus or minus the square root of x. Remember, reflecting over the y equals x line, that gives you your inverse. So here's our parabola over the y equals x line, and it looks like a parabola turned sideways. So this fails the horizontal line test, but look, the plus or minus the square root of x fails the vertical line test, so this is not a function. So what they do is they restrict the domain of your function down here, f of x equals x squared. We're saying x is greater than or equal to 0. Okay, so then we just have this part of the graph. So when that translates, we get this part of the graph. So we get f of x equals root x. X is, that greater than or equal to 0. Okay, so there's our restriction. Okay, and that's what our square root function is going to look like. That's why you don't see the bottom tail of this when we graph, because they've restricted domain. We only see that little top part. But no, that part is also can be there. We just restrict the domain. Okay, so a couple things. We're going to talk more radicals in class, but families of radical functions, you get the square root and then the radical. Okay, so the parent function of the square root is y equals square root of x. The parent function of any radical is y equals the nth root of x. We don't know n, but that's the general parent function. To reflect across the x-axis, you take the opposite. So the negative root x here, it's just negative nth root of x. When you stretch, your a value has to be greater than 1. That's just a times root x, or a times nth root of x. Shrinking, okay, you're just between 0 and 1, but it's the same equation. Translating, same as quadratics in vertex form, x minus h plus k. The h is underneath the radical, the k is not. Those are translations. H and k affect the graph the same way as quadratics or anything. Left and right for h, k brings our graph, our function up or down. So let's look at some examples. What are the graphs of x square root of x plus 4 and y equals the square root of x minus 1? So when we look at the square root of x plus 4, this moves the parent function y equals root x 4 units left. So remember, be careful here. Okay, remember with h, opposite sign, whatever opposite operation is, that'll be what you want to do. This is plus 4, so that means we want to move opposite. We want to move left 4, not right 4. So it's important that I put the parent function in black. So we know we move 4 units left here, so this means if it's subtraction, we're going to move 1 unit right. So in this graph, the function moves the parent function 1 unit right. So let's look. So black here, I have my parent function. I plug 0, 0, 1, 1, and 4, 2. Those are some quick values I can get. So to get the function 4 units left, I take just each of the parent points and just move them 4 left. So here at 0, 0, 1, 2, 3, 4. 1, 1 goes 1, 2, 3, 4, and 4, 2 goes all the way to the y-axis, and there's that red graph. So x plus 4 is here, the square root of x plus 4. Now, the second one, we're saying you move the parent function 1 to the right. So I take my parent function and move every point 1 to the right and draw my graph. So the purple graph is the square root of x minus 1. So the idea with these graphs, you don't have to, but with the translations, you can plot the parent function and move your points accordingly. How many right, how many left, and then just plot them. It's pretty easy to do it that way. In this example, I do the same thing with the parent function. I just move it around, but these are a little bit different. So this example, what are the graphs of y equals square root of x minus 2 and y equals square root of x plus 1? Now you notice the 1 and then 2 are not under the radical. So these are k values, okay? And I've tried to shorten it up. So you be very careful when you're looking if the value is under the radical or not. These are not under the radical. So square root of x plus 1 shifts the parent function up 1 unit, and y equals the square root of x minus 2 shifts the parent function down 2 units. So we're affecting the y values here, not the x values. So when I look at my parent function in black, the first one, I'm going to move every point up 1. So I go from 0, 0 to 0, 1, 1, 1 to 1, 2, 4, 2 to 4, 3, and there's my first graph, square root of x plus 1. That's in red. That's the first answer here. Second graph is going to be in purple. I shift the parent function down 2 units. So 1, 2 here, 1, 2 here, and 2 units down would be on the x-axis, and I draw my graph, and that's y equals square root of x minus 2. So again, these first 2 examples are just translations, moving up and moving down. Obviously, you can have combinations of both, and that's what we'll see in this last example. So the last example has a translation and a stretch, or shrink in this case. What is the graph of y equals negative 1/2 the square root of x minus 3 plus 1? So there's a negative. It's not congruence there, so it's just negative 1/2. So here's the idea. You can choose several x values from the parent function to plot. The parent function is pretty easy. Just pick 0, 0, 1, 1, and 4, 2. That's the parent function. Those are for 3 values for the parent function of y equals square root of x. Secondly, you're actually going to apply that negative multiplication first. So we're going to multiply all of the y values by negative 1/2. Okay, and plot those. So this function is going to be in red. So blue is the original, the parent function. So the red one here is, if I take half of 0, I get 0. Well, negative 1/2 times 1 is negative half. Negative 1/2 times 2 is negative 1. So I go ahead and plot that point, that red graph. That's not my answer, because now I have to apply the translation. I have to move this function 3 units right and 1 unit up. It's 3 units right because I'm subtracting 3. K is positive, so 3 units right and 1 unit up. So the red graph now, I'm going to move 3 to the right and 1 up. So you go 1, 2, 3, 1 up. 1, 2, 3, 1 up. Last point, 1, 2, 3, 1 up, and my purple graph is the answer. So that is what this graph looks like. So if you have any questions or comments, you can type them below. You can email me at nicholas.bennett@dc.gov, and we'll see you next time.